we start with our pseudo-ionone. We mix it with sulfuric acid or phosphoric acid. So, to start off, what's the most reactive thing? Okay. So when we see the H2SO4 and the H3PO4, really all we're seeing is H+. So we need something to neutralize that H+. What do we have to neutralize that H+? So resonance can come into play, so it's not a bad thing, and so let's start that conversation. How is the resonance going to come into play?
The tail of the pseudo-ion.
So the tail of the pseudo-ionone has resonance?
It has the line pair of resonance.
Okay, that's where I wanted to hear. So if we're going through and looking at this structure, we need to find a source of electrons. We could try and pull electrons off of the oxygen because it does have lone pair electrons. Ultimately, all that's really going to do is effectively have the pi bond that the oxygen is connected to the carbon with be reactive. Okay, and so the question becomes, should that pi bond be reactive? And one of our arguments against it is that those three pi bonds are all conjugated with each other. So resonance uber stabilizes them, and by stabilizing them, minimizes their ability to chemically react. Okay? Which then sets us up for the last pi bond to go through and react. How that last pi bond reacts then becomes a potential question that we could deal with as soon as we have it react. Once it reacts, we lose the pi bond, but we now have to explain where the hydrogen goes. The hydrogen can either go to our, how do I want to do it? We'll call it our internal carbon or our external carbon. Right? I know they're both internal, but whatever. Okay, so our green versus our purple. Where should the hydrogen end up?
Internal.
Okay, why?
Because negative anion likes secondary.
Okay, so what you're discussing is the negative anion. Well, the negative anion, there is no anion here. So what you're talking about is, I think, is good. What you're ultimately referencing is that if we go back to our starting material and evaluate resonance of just that pi bond, there are two possible resonances where I can put the negative charge on the, what I'm calling internal, and then the positive charge on the external, or we could have flipped it and done the opposite. And between those two resonance structures, which one is better? The left one. Why? Tertiary carbocation versus the secondary carbocation in our rightmost structure. Or we could look at the anion. We're looking at a secondary anion versus a tertiary anion. Either way you slice it, that's the better resonance structure. Right? In the lingo that I've used in the past, I would reference that blue box structure as our best worst, or our first worst resonance structure. The other lingo I've used is called that the useful resonance structure. The original structure that we started with is our best because everything is neutral. When we're trying to predict something about chemistry, we want to look for that first worst or useful resonance structure. And that one's not our first worst. Okay, so that shows an anion. That anion would predict that my positive hydrogen should go there, leaving me the positive out here. Okay, again, depending on where you go and who your different instructors may be, you may encounter other issues. The issue that typically comes up is that resonance is not a mechanism. You can use resonance to explain why something formed, stable, but you can't use resonance to explain why something reacts. Okay? I still don't fully understand why. So we're going to avoid the why and say, how would you get around that? You would get around that because you could go through and say that your other possibility for this reaction would be placing the hydrogen out here and the carbocation in here. Between those two possible products, The top one is favored because it's a more stable carbocation. Okay? You come to the exact same freaking conclusion, so I don't understand why one is more important than the other. But officially, you're supposed to be evaluating the product stability and saying that that structure is not the best product. Does that make sense?
The ring part, right?
That's the next bridge.
Yeah, but like if it was like that, right, it would be the bottom of the structure, your less stable ring.
So, talking about the ring structure is what's happening after the fact. So, before we can talk about the ring structure, we have to decide what's our major product of that first step. So saying, well, if it continues on, it makes it less stable, isn't going to be relevant to us because it wasn't going to form to begin with. Make sense? Okay. So now we're at a dilemma and say, okay, we have to stabilize this carbocation. How would we stabilize carbocations? Generally, electrons. And typically, where do we find our electrons? In our environment, typically from lone pairs found on nucleophiles. Okay? So we think back through, where do we see carbocations? What mechanism? SN1. And we see in SN1, what's the N stand for? Nucleophile. So typically when we're seeing carbocations, we're thinking we've got to find some source of electrons outside in solution. Okay? And if we think back again to our carbocation mechanisms that we've seen, it's usually a halide floating around in solution. That halide would have come as the conjugate base of an acid. It could have come as the conjugate anion of a salt. Why does this become important? Well, when we talked about that H+, we have to talk about where it came from. That H+ came from sulfuric acid or phosphoric acid. It did not come from something like HBr. HBr is equally acidic. Why not use HBr? The conjugate bases, or the conjugates in each of these cases, all have different properties. The sulfate and the phosphate are what are known as non-nucleophilic. Why? Resonance. The bromide is absolutely a strong nucleophile. And if it's a strong nucleophile, what's going to happen? The bromide would react with the positive and stop our reaction. So if we're thinking about reaction design, the choice of our reagent here becomes really, really important because we don't want a nucleophile to come in from the outside. We want our quote-unquote nucleophile to come from inside the structure. Kind of make sense? We're still laying into this single step, so let's push it a little bit further. What mechanistic step did we do? Okay, so we might go through and say it's acid-base because all we did was transfer a hydrogen. But that's not all we did. In the transfer of that hydrogen, I also lost a pi bond. And if I'm going to lose a pi bond, that's now an addition. So that's an addition mechanistic step. Okay, what kind of addition was it? Well, what was the thing that caused the pi bond to break? It was positively charged. Positively charged things we call electrophiles. Okay? Kind of makes sense? So cool. We've now flogged that single step kind of to death as far as all the individual components that go within it. All of that content is information that we should know about the chemical reaction. You just decided to show up? Oh. That's good. That we should know prior to the reaction, which means where should this content show up? This is all part of your introduction in your lab report. So by driving through the mechanism and now explaining the gory details of why all of these things were done are all part of your introduction to your lab report. Yay! So we're actually kind of opening a discussion on lab report. Not quite yet. We're going to get through the mechanism first. Okay, what happens now? How can we stabilize that carbocation? We again need electrons. So where can we get electrons from? Okay. Pi bonds or lone pair on the oxygen. Again, if we pull electrons from the lone pair on the oxygen, it's going to effectively be pulling them from the pi bond. Okay. If we propagate that out, what we should now start doing is considering what that would mean. That means the oxygen is going to get connected to my carbocation. The carbocation is still connected to this, 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 connected to this. Which then means I form a 10-membered ring. Are 10-membered rings stable? No. Okay? So while the oxygen does have the potential to act as a nucleophile and flip back to attack this, that's going to form an unstable product, which suggests it's not going to happen. Okay? Is that important information that I should address in my background information? Yeah, probably. Okay, now we got to back all the way through all that numbering. Okay, so where else are there electrons? The pi bonds also have electrons. Officially, we just talked about the pi bond with the oxygen and decided that was a dead end. We could then go through and look at how many atoms would be in our ring if we looked at any other pi bond. Okay? As we go through and count those out, what we'll find is only one pi bond produces an optimal number of atoms. Okay? That pi bond needs to somehow do a chemical reaction. What flips most students out is that that seems insanely far away and impossible to happen. Okay? But what we have to realize is what can happen. So before we launch into the mechanism, it might actually make sense to do our sigma rotations so that we can see that it really isn't that big of a deal. And sorry for the quietness, I've got to make sure I don't lose track of my carbons. Which becomes easier if we freaking count. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. 6. And there's my carbocation. Why did we count? Why did we count out and put all those numbers on it? Make sure who didn't? You, the person doing the action. Which means if you were going to put this into a report, do you really want to point out that you can't keep track of your carbons? Probably not. Okay? So if you're going to now try and publish this, you would probably hide the fact that you can't keep track of your carbons by not actually numbering them. Does that make sense? Okay. Formally, I don't care. I'm not going to dock points if you count in your actual mechanism. Okay, but just things to consider. What's now going to happen? Your pi bond can react with the carbocation. Okay, we've already set up a system where we know which carbon it's going to be because of how we've drawn our structure. We can go ahead and color code that, I guess. And we'd have a structure, right? No, why not?
Charge.
We forgot the charge, of course. Okay, when that pi bond came out, we're taking the electrons from the pi bond and connecting it between carbon 1 and carbon 6, which means carbon 2 lost electrons. it needs to be positively charged. Kind of, sort of? Okay. Now what can happen? Okay. A variety of things can go through and continue to happen within this. But actually, before we do that, we should double back. The sigma rotation was just a rotation. We didn't do any chemical reaction there, so we don't have to explain anything other than a sigma rotation. But we did do a chemical reaction on this last step. What chemical reaction did we do?
Ring formation?
We could call it a ring closure. Okay, so language-wise, that's fine. That doesn't fit the patterns of what we've talked about within our lecture. What was the mechanistic step? This was officially an addition because we lost a pi bond. When we lost that pi bond, what did we add to it? A positive charge, which means don't worry, no one heard that in the recording. We now have, I'm actually serious, no one heard that in the recording. All right, we have our electrophile addition. The only way anybody would know that you said anything is if I said your name, like Tyler. You feel better?
No.
Or worse?
You did.
Okay, so in any case, we now have a carbocation, so now we should consider the potentials for rearrangements. Okay, so we could go through and launch into our rearrangement system. Okay, where are we going to rearrange?
To the tertiary.
We've got a tertiary spot right here, as long as we remember the implied hydrogen. So we can do the rearrangement. I'm only looping over to the other side just because it's so tight within that spacing. Okay? And I'll say it again just because some people question the curly Q. I throw the curly Q in there only as an extra note that I'm doing something goofy like a rearrangement. And we've already stated what this was. We said this was a rearrangement. Could we get a little bit fancier behind that, calling it just a rearrangement? Technically, yeah. It's not that big of a deal. You said yeah. What do you think, Gage?
Isn't it like a 1,2 hydrogen ship?
Lovely. 1,2, and not hydrogen, hydride, because it's moving with the electrons. Fantastic. Okay? So cool. We've done that rearrangement. We have a 1,2 hydride shift. Now what?
We do another, or we want to get rid of the positive charge.
Cool. So we could consider resonance. That's actually why we did the rearrangement. We moved from a tertiary structure to a tertiary plus resonance. So that helps to explain why we were allowed to do that rearrangement. We could look at the resonance structures. Ultimately, those aren't going to do a whole lot to permanently stabilize the positive charge. We need to permanently stabilize it. How can we permanently stabilize it?
The iodine itself is acting as a base at the beginning.
You're not wrong. I just don't like your statement because you're asking me to now draw a pseudo-ionone again.
I gave it pseudo-iodine.
Okay, so ultimately, really what you're saying is that what we need to do is what?
An electrophilic elimination.
You're cheating and look at your notes.
No.
We need to do an elimination. Okay, that elimination can permanently stabilize our carbocation by removing the hydrogen. So we can look at the hydrogen at the beta position. Okay, again, this is crowded, so we're going to see a big long arrow here. But our base, I've been trying to sort of color code. Anything remotely basic can come in and pick up that hydrogen, and we can shuttle the electrons over. Note that I'm pointing that arrow at the bond, okay, to make our pi bond. I'll draw that structure in just a second. I want to highlight the fact that our base does not have a negative charge. Why not? I'm under acidic conditions, so I don't want to show any actual negative charges. So I can show that I have a base, it's just a weak base, just a lone pair of electrons. All right? So we can now navigate to our product. When we did this elimination, when we formed that pi bond, what was eliminated from the structure?
The sigma bond between hydrogen.
What charge was that hydrogen? Positive, which means what kind of elimination was this? This is an electrophile elimination. Kind of makes sense? And we now have a product. Yay, we're done. No, we're not. Okay, but we're pretty exciting done. Okay, this structure is what is known as beta ionone. I do not know why they call them alpha, beta, and gamma. For the record, I thought I had an idea and I was proven wrong. Okay, so we do have different ionones. Okay, those ionones all are the result of an electrophile elimination, but that sets us up with a bit of a problem. If we take a look at that carbocation, the step right before this, what beta hydrogens do we have? 2 beta hydrogens? You're taking pictures. I think you're a bit premature, just for the record. It rhymes with what everybody is having right now.
You're the Riddler?
There's only one, guys.
There's one? But no, wait, there's another one, right?
There's the carbocation, right? What's down here? No implied hydrogens. What's up here? No implied hydrogens. What's over here? There is an implied hydrogen here connected to an sp2 atom. That's not going to be a hydrogen that you can remove easily. That hydrogen is now drawn into its structure and you're not going to pull that one off. Which means only one beta hydrogen. If there's only one beta hydrogen, shouldn't there only be one product? Yeah. And yet somehow we're supposed to get 3.
That's assuming that it went through the hydride shift, right?
There it is. What we're assuming is that it did the hydride shift. What if oh God, I drew that so horribly. Let's try that again. What if that structure, our original carbocation, our tertiary one, was able to eliminate faster than the rearrangement? Are there other beta hydrogens from this tertiary carbocation? Yeah, there's actually. Depending on how you count it, I guess. Okay. We have the hydrogen that we already tackled off of that, okay, for our rearrangement. And if we removed that one, that would just result in the beta ionone. Meh. We already drew that. Let's not worry about that one. But where else do we have hydrogens?
Next to 2.
Say again?
There's 2 next to it.
Right over here. I have beta hydrogens over here, which means my base could come in, remove that hydrogen, make my pi bond. This is going to be another electrophile elimination, which I'm just going to abbreviate as capital E, capital E. And this sets me up call that there. With the pi bond there, this is known as the alpha ionone. Well, we said there were 3.
On the hydride one that we did, it can.
You don't want to look at the hydride one. Try again. Where else is there a beta hydrogen? It's on the methyl group right above. So our base can come in, remove that hydrogen. I tried to make this as uncrowded as possible, but I fully understand that this is crowded. It looks even more crowded when you zoom out and see everything, which is what you guys get to look at. I'm sorry. And we get our gamma ionone. Okay? Of those three products, do you like any one more or less than the others? Why do you like the beta ionone?
Follows the most expected route.
Okay, I can accept that. Why else might you like the beta ionone? If we look at the beta ionone, it's the more thermodynamically stable. It's the most substituted one. Okay, I would push on that even further because I didn't see that. And for the record, I didn't put in the recording your statement, which was also good, that it's following the most expected route. Okay, because we're seeing that rearrangement. That makes a lot of sense. More substituted and conjugation. We get the resonance with that system. Okay, that resonance, I would argue, becomes a pretty big deal. Because if we have resonance within that particularly more resonance than it has in any of the others, what is that going to do to where we would see those bonds appear in IR? They will shift. Okay, so if we're looking at our IR spectra, if we're seeing a significant shift of the carbonyl and carbon-carbon double bonds to lower numbers, that's pretty decent evidence that you're seeing the formation of the beta ionone in preference. Okay, it's not perfect, but if that's all we've got, that's all we've got. Does that make sense? Okay. Do you see any particular product as being like, God, no, it's not that? Why the gamma?
Just looks wrong.
Okay. It is unstable because it's a less substituted product. Okay? So the gamma ionone is very unlikely when we look at kind of the thermodynamics of our overarching system. Okay? The gamma ionone, though, is pulling off a hydrogen that's most accessible. Based off of what we just talked about with our elimination stuff, it probably still doesn't make sense to be pulling off the gamma because we're forming a carbocation. That should be our E1. Okay, so the gamma ionone has a much lower probability of actually being formed. If you consider the previous conversations that we've had kind of within this, not within this video, of course, for people listening to the video, we talked about the ratio of the ionones in that table. Does that sound vaguely familiar? That was the ratio of what ionones? It only listed alpha and beta because gamma was very unlikely. Okay, kind of makes sense? So this is now kind of our entire mechanism all put into gory detail. We've addressed lots of content verbally through this video that can't or could, but we're already crowded enough as it is, could get written onto this. Like we said, why do we want the beta ionone? It was a more substituted stable double bond. And it had resonance. That is an explanation that shows an understanding of what's written down. Where should that explanation in words appear? That needs to appear in your introduction. So when we're talking through this mechanism, okay, one of the big expectations of the introduction is that you're going to explain how the reaction works. That's the mechanism. But you now need to not just show it, but actually use words to explain it. Just copying this down as your mechanism isn't sufficient. Okay? And I would argue copying this down is excessive. There's a lot of stuff in there that you just don't need to show in a mechanism. You would need to explain with words. Does that make sense? Okay. Which kind of sets us up with the next thing. If you're going to go through and explain it in words, should you provide the entire mechanism all nice and clean? Can I erase stuff? Oh, let's see if I can be careful. Whoops. This would be a good time to pause the recording. Instead, I'm just going to kind of talk through it, and you can listen to my sounds of my soothing voice. Five hours, nearing 6. If we talk about an overall mechanism, does it make sense just to draw this out nice and pretty and then just be like, now write your paragraphs talking about this whole thing? Okay. This is now going to be a logistical choice. You get to decide. Does it make sense to do one step, explain the details, then do the next step, explain the details? Or do you just go, there's the whole freaking mechanism, now I'm going to explain all the details? That is up to you to decide. Okay? Within that decision, I do want to volunteer some information. If you're going to do it as one big thing, that's fine. When you go through the text to write it out, it should not be one big thing of text, because you're changing topics as you navigate. You're going to talk about the first step. Then you'll talk about the second step. You should have paragraphs. Why do you have paragraphs? But why do we need to separate topics?
Keep it clear.
It helps for clarification. There's another big reason. If you've ever just read a book, right? When you flip to a page, have you ever flipped to a page where it's just text with no paragraph breaks? What do you immediately do?
Roll your eyes and start.
What the hell is this? This is dumb. I don't want to read this anymore. Stupid. I got to read it anyway. Okay? Guess what a grader does when you do that to them?
They check out.
Okay? They're going to do the exact same thing. Okay? So paragraphs, yes, keep clarity, but they also give your reader a break to breathe for a second and to refocus and restart. Okay? So you want to be cognizant of that when you go through to put together a lab report. Because if it's just a wall of text, you're going to piss off the grader. A pissed off grader generally means they find things to subtract points for. Okay? You don't want that. What you want is a relaxed, chill grader that is just like, oh yeah, this is easy to read. And they float through your document. The process of floating through the document means they will make tons of mistakes in your favor. The slower someone grades, the more accurate the grade, and probably not in your favor. Okay? So you want to set up a document that allows people to scan through it quickly and efficiently so that they don't see that you don't know what you're talking about. Kind of make sense? Okay. Questions about the mechanism? And I don't know if you remember last Thursday, but I was like, it's the methyl group. That's all it was. That's all it was. I just deleted that methyl group and the whole thing fell to pieces. See how important technically 4 atoms are. One line changes your ability to answer a question appropriately. So be careful with your notations. Okay. We'll take a hot second break here. At least I'm going to